How to position 3D objects. Welcome back to SelfCAD. You're watching part 2 of our 3D Modeling 101 series. In part 1, we explained what makes an object 3D, and in this one we will teach you how to position such objects within a 3D workspace. Positioning is a fundamental skill for any designer, because you will need to know how to select, align, and position objects, or parts of those objects, to manipulate them to your liking. But before we get to that, let's have a look at how we position physical objects, and then compare how we do the same in digital 3D software. How do we position physical objects? We'll use one of the most prominent spaces in our daily lives as an example: a room. Imagine for a moment that we have an empty room, and we'd like to add some furniture and fixtures. Typically, you'd start by measuring the size of the room. Then you would divide the length and width in half and mark those places as the center positions. And now that we know the layout of the room, we can start decorating. Say you want to hang up a light. Once you have the center position, you could measure the correct placement as a distance between the ceiling and the floor, and then hang the lamp accordingly. Once you have the correct position, you could measure the correct placement as the distance between the ceiling and the floor, and then hang the lamp accordingly. Now, if we analyze this scenario, you can see we just used the room as our 3D workspace. You can see how the height differed from length and width in the sense that we did not care about the actual height of the ceiling, as we only measured its distance from the floor. It might seem trivial, but it teaches us an important lesson about reference points, commonly known as the pivot. What we just did was focus on the center of the room as the reference point to hang the light. In the mathematical sense, we measured the distance between the center of the light and the center of the room. The center, however, is just one of many possible reference points, aka pivots. We could use the ceiling as the main reference point, just as well, and the top of the light as the second one. Or we could use the floor as the main pivot and the bottom of the light as the second. One thing to note is that we used 2D measurements to position a 3D object in a 3D environment because we focused on a single reference point at a time. Now, digital 3D objects within a digital 3D environment follow the same concepts. You just have to use features that will move the objects for you. There is, however, one big difference between positioning objects in the real world and CAD workspace. It's the simple fact that physical objects can't levitate on their own, so you need something to fasten the light to the wall, while digital objects can float in midair, as there's no concept of gravity in 3D modeling applications. How do we position digital objects? For this part, we'll launch the SelfCAD editor and start by setting up the workspace, also known as the scene. You cannot move the object outside of the scene, and you cannot make the object bigger than the workspace. So if you need more space for your project, you will need to increase its size. The scene acts as a digital room, so we don't have to measure anything outside of its borders. Those constraints help us manage the assets in the workspace, but they also make it easier to transform those objects, as we'll explain in a minute. Setting up the workspace is similar to how we perceive a room, but positioning objects inside the scene is much easier. SelfCAD uses a Cartesian Coordinate System that automatically calculates the center of the scene, as well as the center of all objects that we use as pivots for transformations. But before we move on to transformations, let's look at what the Cartesian Coordinate System is and why it's so important. The Cartesian Coordinate System. The Cartesian Coordinate System is primarily a 2D measuring system that uses a 2D plane to calculate positions, but it's possible to extend it and apply it to a 3D environment. In SelfCAD, we combined multiple 2D planes to create a 3D scene, and thus calculate positions in 3 dimensions. Let's see how it works in 2D first. We'll start by drawing a rectangle and label the sides as X and Y axes. At this point, we have 4 edges that create a closed loop, and once we fill it, we get a surface, also known as a polygon. Now let's subdivide it by drawing a center line in both directions, which will subsequently create an intersection at the center of the surface, giving us a center point. We label this point as 0, 0, which will serve as a pivot, allowing us to measure position in all directions from the center. Let's have a look at how measuring positions in this way differs from measuring the room with a ruler. Using a ruler versus a Cartesian coordinate system. A typical ruler has only positive numbers, and regardless of the direction you measure from, you always get a positive value. For example, if we have a square room with a size of 700 meters, and you would like to position a lamp at the front left corner, you would have to tell the contractor to place it 50 meters from the front or 650 meters from the back, and then add the position from the left or right wall. This, of course, makes it difficult to explain with simple annotations, and becomes problematic when working with more complex structures. Consider if you'd like to position the same lamp within an octagonal room. You would need to find a way to label each side so you could reference them for the contractors, which could be even more impractical. And that's where the Cartesian coordinate system comes into play. By using XY as coordinates, we can find any structure into a square, which is a concept known as a bounding box. Digital 2D software automatically creates a simple rectangle around the scene, isolating everything within a square. The main advantage of the Cartesian system is that we can start measuring from the center. We divide the plane into positive and negative sections so that we can use the idea of a bounding box even without extending the room or drawing the rectangle. The Cartesian coordinate system consists of 4 rectangular sections called quadrants. Here's how they work. We have 2 axes, x and y. First, we label the direction between the front and back sides as the y-axis, and mark the front as positive and the back as negative. Similarly, we mark from the center to the right as positive x and to the left as negative x. The front right section is considered a positive because the front and right are both positive. The front left is positive negative. The back right is negative positive, and the back left section is negative negative. How the Cartesian system works in a 2D plane. Now let's go back to the previous example. How do we position a lamp in a 700 square meter room using the Cartesian coordinate system? Let's say we want to position it 50 meters from the front, which is our y-axis, and 50 meters away from the left side, which is our x-axis. We would annotate those positions as y 300, x negative 300, because the front side is 350 meters away from the center in the positive direction, and the left side is the same distance but in the negative direction. This same concept can be used for an octagonal room or any irregular shape, because we don't need the outer edges for measurement. We only measure from the center and use quadrants for directions, so there's no need to define all the sides. The Cartesian plane is also infinite, so we can use it to get the position of any random point as long as it aligns with its 2D plane. We just covered the 2D plane, but as we still need a solution for measuring 3D positions, let's take a look at how they work in SelfCAD. How the Cartesian coordinate system works in a 3D workspace. We can also use the Cartesian coordinate system to measure objects in 3D space. In the previous example, we only used 2 coordinates, x and y, to show how it works in 2D. Now we'll show you how we expanded the Cartesian plane by adding the 3rd dimension. The concept is similar to how we position objects on other flat surfaces, such as the floor of a room or the top of a table. If you want to place a lamp on the floor, we can assume that the height is 0 relative to the local 3D environment. On the other hand, if you want to put a glass of water on the top of a table, we adjust its position based on the height of the table. In both of these cases, we can only focus on the XY axes and ignore the height, because it's constant and will not change as long as the object stays on top of that surface. It allows us to continue working with a 2D Cartesian plane and use the 3rd axis as an offset from the surface. Let's use our lamp example again. When you place the lamp on the ground, you can focus only on two axes, as the height will always stay the same. However, once you want to hang the lamp on the wall or from the ceiling, you will need to measure the distance from either the floor or the ceiling. The same concept applies to 3D software. The Cartesian plane is always the primary 3D scene, but you can always change the height as an offset from that plane. You can actually add an infinite number of Cartesian planes within a single scene. In SelfCAD, some features such as 3D Sketch work best when adding additional planes. But for the most part, we're using the default plane with the position 0. It's also important to note that SelfCAD does not allow moving objects outside of the workspace. And because our floor plane has the height 0, you can only place objects above it. Why do we need a primary plane when working with 3D software? There are technical reasons why we need to work with a primary plane. The main reason is that it helps the application understand the positions between objects we are working with, and particularly how they can intersect with each other. 3D software like SelfCAD uses algorithms that help it find the objects you're clicking on, which often rely on intersection planes, and it is why we get more flexibility on the primary plane. For example, the transformation tools like Move, Scale, and Rotate offer you more directional gizmos, while Height has only one simple up and down gizmo. The same is true when you drag and drop a new shape from the primitive generators or from the Objects panel, as a way to make a copy of an existing object. In both cases, you can freely move the new object along the floor, but to change the height, you'll need to enter the Move transformation. That's because the floor is the main intersection plane, and all new shapes will snap to it by default. XYZ Coordinates in SelfCAD. You may have noticed that we refer to the Cartesian plane as XY, so the height would need to be the Z-axis. But as you can see, SelfCAD labels the height as Y and the main plane as XZ. It doesn't really matter how you label each side. You just have to be consistent throughout your entire project. Some software labels the height as Z, and some flip the Y and Z. SelfCAD gives you both options. You can set the orientation when creating a new project or change this later in the Workspace Settings. Before we wrap up this topic, let's go back to the lamp example one last time. As a 3D designer, you'll encounter times when you'll need to measure distances from the center of an object. Measuring from the top, bottom, or any other location is pretty straightforward, but finding the center of an object requires a little bit more skill. First, we need to understand how we measure objects. It's easy to locate a single point at any location in a 3D space, as we described at length in our previous examples. But when dealing with objects that have mass, it requires us to use the bounding box logic. To remind you, the bounding box creates a simple rectangle around the entire 2D or 3D scene, which helps isolate everything within a square. With 3D objects, it creates a virtual box that wraps around selected objects and calculates the center point by itself, marked by the position of the gizmo. That's it for part 2. We hope you now have a clear understanding of how to position objects in a 3D space. Next, we'll show you additional measuring and positioning techniques, and finally, explain how the camera works along with basic transformation tools. Thanks for tuning in, and we'll see you in the next video.